Okay. And before we start our presentation, I'm going to turn the meeting over to Doug Rothenberg to introduce tonight's presenter and our topic on transducers, filters, wave motion, and music engineering by John Mihevic. So, Doug?
Thank you, Ryan. As said before, John is retired from NASA. He started in the Rocket Systems Division at NSA Plumbrook, and I visited that a long time ago, and I was surprised to learn that they were testing jet engines, but they were pointing towards the ground. And after about 10 seconds, it made sense, because when you fire these things off, you don't want them lifting off, you just want to measure their force. When you point them down, you can keep them in place. He also worked at NASA in Brook Park in the process control systems. He was the manager there for that group. He holds a Bachelor of Science with honors at Electrical Engineering from Case Institute of Technology, my alma mater as well. He holds a Master's of Science in Mechanical Engineering from Case Institute of Technology. And John has been basically part of the glue that holds the Cleveland section together. He's a longtime member and very active in the leadership, and we owe him a debt of gratitude for that. But I think we're going to be very interested in the presentation today. John, I will turn the meeting over to you.
John, if you're speaking, you're on mute.
Hey, can you hear me now?
We can now, yes.
Okay, let me see here. I got a bunch of initials. Wait, let me get my, okay, can you see the PowerPoint?
We cannot, so you need to...
I've got it on my, oh, I got to share, don't I?
Yes.
Or something. Oh boy, wait a minute. Oh, share tray, okay. Back to PowerPoint. Can you see it now?
Not
Just to let everybody know, John is working off of 2 cameras, so we can see all the equipment and we also can see him.
Yeah. And I want to point out that Ryan has to do a lot to switch because he's got to go in some spotlight mode and go on the camera.
Yeah, I'm not.
Anyway, can you see my first screen?
I am not seeing your screen.
Oh boy. Wait, do I have to, what else should I try to do here? Camera off,
on your
close the share tray. It says close it. It must be, should I close it
no,
and open it again?
In your share tray, you should see your PowerPoint. You either want to click on the desktop or the actual PowerPoint so that we can see it.
Wait, open share. Okay.
You got to tell it what to share.
Let me, is this it?
Like we did on Saturday.
Can you see it now?
Yes, now we can see it.
Okay. Well, I'll get
There's
started here. Give you a,
before you begin, in the little Teams window that you see there in the corner, if you minimize that, that will allow it to be full screen because it's, yep, perfect.
I minimize that.
You're good. You're good.
I don't see my camera now, but I guess I don't need to. I was seeing it before. Well, that's okay. No, anyway, to start off, my interest in all this goes way back when we
You're not John. Your PowerPoint is not main screen.
it isn't.
No,
Uh,
the camera on your equipment is main screen, and it looks very enticing.
well,
It should be.
uh,
That's what I'm seeing here. Is it that way for everybody
I'm
else?
seeing the PowerPoint okay.
Okay.
oh,
Okay.
Yeah, PowerPoint.
Yeah,
I
you have
see
to
the
click. If it's
PowerPoint.
on the side, you have to. Each of us have to click on it. Didn't
Yeah,
realize that.
there's some
Okay.
choice by the user. Yeah.
Viewer.
Is everybody? You have it, Doug?
Yes. So what it means is that when you start to demonstrate, we have to click on the equipment, and we'll click on the PowerPoint while you're PowerPointing.
Yeah, and I don't know what you're going to have to do with the camera, but I think
Just
it'll-
click on the picture.
Yeah,
When we're ready
no.
for the go to the picture, you tell us to go to the picture, and we'll go to the picture.
Yeah, no. Look, I got a fair amount on the PowerPoint here, so I'll get going. Anyway, to back up, my interest started a long time ago. Basically, when we got married, it was before I started NASA, and my wife complains to this day that our first piece of furniture was an old Hammond organ, 1937, that I got for $900. Anyway, so I started NASA 66, and then it was about 67. And, you talk, word got around that, I was working on this old organ, and people always went on the surplus list to see what you could get. You could order anything if you're in the government for surplus, and it was free. You just had to put the request in. Well, this fellow found at an Army base in Arizona a Hammond console organ in a tone cabinet, Hammond tone cabinet. So he had it shipped to Plumbrook in Sandusky. So all of a sudden, one day I get a call, and they say, geez, we got this organ in here, but the cabinet's busted, the back's off. The bottom strut going across was missing. And can you take a look at it? Well, okay, so I went down there, and oh my, there's the shelf with the amplifier, and believe it or not, it's a tube amp, and all I saw coming out the power supply side was wires. It was dropped so hard that the power transformer was ripped off the mounts. I looked for it, it was down underneath, and then another thing, and aside, the tone cabinet had reverb. Hammond developed the first reverberation. It was what they call a spring reverb. Well, it was a necklace type, and they also dropped the tone cabinet. And all the springs, there's 3 of them, it was a necklace, were wound around all the magnets. So that was a lot of fun getting that apart. And basically, I got it all together, and then, you learn stuff when you have a problem. If you just buy something and it works all the time, you don't really learn anything about it. So that's what's got my interest, because I really had to dig into it, and I learned a lot about it, and basically it just had a lot of basic stuff, physics, math, and just all the basic tools of engineering. So that's what got me going, and I'll get on here now with the program, and a brief thing of what we'll be seeing here. And thanks to Doug, I didn't know how to do this, bringing these little pictures up. But anyway, we're going to start with the single tone of how Hammond developed his tone wheels, and how he there's a speed pickup there that is basically, you know, what we've used at NASA a lot. A lot of industries use them. And then the synchronous motor, that's a pic of it there. And then, well, we'll get into this deeper later, but basically Hammond machined an octave of gears for every halftone and machined them right on to the halftone frequencies, but I'll get into that detail. And then the pure tone is just kind of dry, you know, without any theater effect. So to give the music some interest in tremolo, I go through two things here. The vibrato scanner on top, which is like an electrical Doppler, and then the rotating horn there, which Leslie is an acoustic Doppler. And then I'll go into how the tones get generated, go through the key contacts, and then that's the back of the Leslie speaker. So see, for schools and demos, I split this whole thing up: tone generator, amplifier, and speaker. Well, I couldn't do a 15-inch bass speaker, so that thing you see to the left is my Leslie. It's a 6x9-inch bass speaker that doesn't really do much to it, but that treble horn is identical in both. And let's see, I think I've got this pointer here. Yeah, okay. Just to point out in this, just the bass speaker, back here is the crossover, so that you know the output of the amplifier comes into a crossover, and then it gets split here at 800 hertz. Above 800 goes to the rotating treble horn, and below goes to the bass speaker. And this is a rotating bass drum down here. But again, we'll get into more detail. To start out with, the basic speed pulse transducer is basically a magnetic rod inside of a sensing coil. And you have a rotating gear that distorts the magnetic field and causes an induced voltage in the coil. And Hammond shaped the gear so that he would get sine waves, but the wave output is really depending upon the shape of the gear. I mean, you can have square teeth, which actually I've seen in cars on the that pick up that rotating. It's usually inside the rotor for ABS braking. The one thing about this, it's passive, it's low output, and it's said, like a lot of times at NASA, it'll send to a signal conditioner. I always remember one example was our turbo expanders that turn at 10,000 RPM, and what they really do is take high pressure air and take it down to very low temperatures at 10 PSI. But we had to monitor the speed, and if I remember the shaft, they just cut grooves in the shaft at 180 degrees apart, and it was really hard to get a signal. We did, but then we went into a signal conditioner for signal shaping, and of course, once the signal conditioner picks it up and converts it, then we go into a regular 4 to 20 milliamp output, and you get pulses proportional to speed. And real quickly, that's the basic system that's used on all your ABS on cars. You know, it's a control algorithm, uses the speed wheel sensor, and it controls the output to the braking system, to the hydraulic valves. And you know, if it picks up a wheel going slow, then reduces the it's detection rotating slow, reduces the hydraulic pressure to the brake. Boy, if I got that backwards, the detection of the wheel rotating faster than the rest. Well, got to think about that. You know, I might have that backwards. Basically, it's looking at both, and if the wheel's going, if the wheel's going too slow, okay, it reduces the hydraulic pressure and the wheels speed up. Yeah, this is right. I better stop thinking about this. Anyway, the hydraulic pressure can go at a rate of up to 15 times a second. Okay, now the music application of the pulse generation. This all started in 1933, the Great Depression, when Hammond started looking at this. Organs were real popular in churches, pipe organs, but they were expensive, $75,000 a piece. And there was a need for a cheaper electronic alternative. And all you had basically, the technology in the times in the 30s were tube oscillators. And you could build a tube oscillator and get tones out of it, but you know, drift was really a problem. So you needed, and we didn't have, you know, quartz oscillators or anything for a stable reference. So Hammond, who was an inventor, he built all kinds of things. If you want to ever look up, he built card shuffling tables. He built just a number of things, and a big thing was his synchronous clocks. And you know, that was a big thing. The wind-up clocks didn't keep time, and the synchronous clock would lock onto line frequency. And he sold a lot of them. I think he sold them all to the post office too, across the country. You know, so they were locked in the real time. But at $3 a clock, his profits were low, and it was the Depression. So he's thinking he's got a real stable frequency reference. He says, how about my clock motor? And so now he's got the clock motor for stable rotation frequency. And he's thinking, well, what if I turn the rotor and use the rotor cogs to cut through a magnetic field? And I might add that 1937, the first Hammond I had, you know how it says the Hammond organ or that? Actually, the organ said the Hammond Clock Company, a little aside there. So this is the basic thing here is magnetic pickup, a tone wheel. This is a tone wheel of 192 teeth. And over to the left there, you see that'd be just a diagram of the tone wheel rotating. It'll cut the magnetic field. That's a chisel point on the magnetic pole. And you'll get millivolts output from this. And this happens to be one of the highest frequency tone wheels. Let's go on to the next one here. Here's an example of the extremes. Here's a 2-tooth wheel, 128 tooth and a 32 tooth wheel. An interesting thing you'll see later, and you can see the shape of those, the 128 and the 32 tooth wheel. They're shaped like sine waves. And there was a lot to the design of this, you know, to get a nice tone out. Now, the 2-tooth wheel, let's see, how do I want, I'll get in. The 2-tooth wheel is used for the pedal tones, the bass frequencies from 32 hertz to 64 hertz. And there's only, this is, well, I'll get into it. It's a drawbar organ. You'll see how by additive synthesis, he uses 9 drawbars to get all different tones. Well, not in the pedal. The pedal only has 2 drawbars. Well, when his first organ had just a sine wave, and it was just a dull, crummy tone. So if you notice, and they call, Hammond called this his complex tone wheel, the sharp step. Well, really, it's generating a little bit of square wave with more harmonics. So it's kind of slick how he did that for the first octave of pedal tones. Those don't go into the keyboards or manuals at all. Okay, now I don't want to get involved too much in his calculations, but give an overview here. The demo I have, it's a little keyboard, and it's only one keyboard from a spinet organ, and it's 44 keys. Now, the full-size organ has, well, the spinet has 2 keyboards and 44, but the full-size has 61 keys, and the pedal board, so you need frequencies from 32 hertz to 6,000. And Hammond did it really with the tooth wheels, 2, 4, 8, 16, they double every time, 64, 128, and 192 teeth. The 192 is 7.5. He could really get 8, but I don't know the reason. He got 7.5. He uses the top half octave is the 192 tooth wheels. So you have a tone wheel in each octave, but then in each octave, he divides that into 12 equal parts to get the chromatic scale. And it's the equal tempered chromatic scale. And he basically does that all with gearing. I just, because it gets involved with the math, I just wanted to point out here, and if anyone wants to, is interested, by the way, I'll send my PowerPoint to anyone that wants it, but you can go through the math. This is basically if you have any interval, and I took this, a simple one here, say you want to put something in at 3 inches. Oh, no. Start at 3 inches, end at 9 inches, and you want it to be 4 divisions. Well, the rule you do is you take the ratio of the end point to the starting point, 9/3 is 3, and you raise 3 to the root of the division, so it's 3 to the 1/4. And anyway, if you just look real quick here, your first one will be at 3 inches. Then I just show pegs there if you want, for some reason, to put pegs in the hole. Then 3.948, 5. Anyway, so on down to 8.99. So that's how, excuse me, you by math get the divisions. Now, let's see what I want to take out of this one. There's a lot of math here. Basically, for music in the chromatic scale, you have 12 divisions for the 12 notes. So the, and it's an octave, so the end point is twice the starting point. So it's the 2x over x is 2. So 2 is the power you have to raise the root to, and it's 12 divisions. So it's basically 2 to the 1/12. And that number, yeah, 1.05946, it's an irrational number, is the space between each halftone. So, you know, from like there I show C is 32.7 hertz. C sharp, that's the next halftone up, is 32.7 times that number. And that's the next tone. And then you take the 34.6 and multiply that by the number, and you get D. So you got C, C sharp, D, and you just keep doing that all the way up till you do an octave. And then I've got speed oh boy. I've got speed calculations here. I won't go through it. It's just cancellation of to get the speed. And so the bottom line is here, at the same speed, we can use 4, 8, 16, 32, 64, 20, 128 tooth wheels. And then the rest of the octave. And then within each octave, the wheel rotating at 12 different speeds. So I won't go through all these numbers, but what's important here in the table is this is an example of one octave. It's the two-tooth wheel. So if you notice, we start here at C. That's the lowest one, 32.7 hertz. And okay, all these hertz are multiplied by that ratio, 1.059. And that gear ratio, okay, one thing I didn't probably point out is the motor on the Hammond is a 6-pole motor. I'll get into that, but it turns at 1200 RPM. So the main shaft speed's 1200. So if you look at all these gear ratios here, let's get the one closest to 1200, 1236. It's E, the note E. It's 1.03. So the main shaft, that gear is, that's the gear ratio, 1.03 of the main shaft speed of 1200. And that's how I get E. And then he goes 0.972, you know, to get the next one, 0.918, 0.866, 0.817, and so on going up. Then going up, you go 1.09 all the way down to 1.543. So the wheel is going from 980 at low C all the way to 1851. Oh boy, I notice part of my screen is off. The next C, and that was to make the point. The thing to realize here is this is one wheel. This would be like a two-tooth wheel, giving all these frequencies by gears. So the basic concept of the whole organ is one tone wheel in an octave and a set of 12 gears in that octave. And it's just used over and over again. Let's see what my next, well, that's pretty much it. Let's see, Ryan, well, are there any questions, or are there any raised hands, or I don't know if I can hear you.
There are not, John.
Okay. If this is okay with everybody, I'll just keep going, or you can ask your questions later. I don't think there was anything else I was going to point out here. Just again, realize that's how he gets every octave with a total of 8 octaves with a different wheel in each octave, rotating at these speeds. Okay, now a little bit into the synchronous motor, and just want to do a little, let's see, I think this is what And this is the basic motor. Took it apart. Those coils really go on those pole pieces to create the magnetic field. And there you see the 6 poles. And that's it. Has no starting torque. And it's, you turn it on and it locks in. Ryan, I think now I'd like to go to the spot, the camera. Can you switch to the camera?
Give me 1 second here.
Each of us have the option to just click on the on the lower side. We can choose camera or his presentation. So each person click on the room view, and you'll get the room view.
But what do I got to get out of my?
No, you're fine.
No,
you're fine, John.
You're fine. I got it.
You can change chairs if you want to.
Oh, I wonder. No, I mean, so I can see the camera.
Yeah, everyone should be seeing the camera now.
But not me, right?
Each individual has to pick what they look at.
No, I just did it for everybody. Doug.
No, I can look at his PowerPoint anytime I want. So we do it ourselves. But go ahead, John.
Well, the thing I need, Ryan, it says no preview available, webcam, another application. I need to see the camera so I can zoom. It was like at the beginning, what do I do? Or
You had it minimized? Or you minimized it?
Minimized what? The PowerPoint?
No, the Teams window, right? That's what you're...
Oh, the team window. Oh.
If you bring up the Teams window, you should see the feed from the
Teams window.
From the camera, which is a little pixelated at the moment.
Yeah, I might have to. Okay, let's see. How do I? Which one? I got 3 windows. Cleveland section RK. I lost it. Okay, I got RK. I got a RK,
John, can you just play the instrument without zooming, and I think we'll get the gist of it?
Oh, no. I got this camera special for this. I really need this.
If you click it in the middle of that window, John,
okay.
It should make it full screen.
Turn camera on.
We just lost the camera when you just did that.
Oh, jeez. You lost the camera?
Yes, we just lost the camera feed.
I've got it over here. What do I do now?
Okay, so...
Where's your shared window? Sharing is paused until you return. So I got to go back, and then if I share it, maybe? Oh, boy.
Okay, so right now I am seeing what looks like it's a PowerPoint, your PowerPoint.
In the corner.
Right, and it's, well...
Should I close the PowerPoint?
No,
because I can get back in real quick.
John, can you undo what you did to turn the camera off?
Yeah, it looks like he's turned the camera off from what I am seeing here. Unfortunately, I can't.
Well, it says my Brio's connected. Let me try. I'll close it and restart the whole thing. But see, it's connected to me, not to you. Okay, I'll close it. And now I'm going to reopen the camera. Okay. See, all I do is get it back to myself. How did we do this? I could log out of Teams.
Can you drag that to a different window on your computer?
Me?
Yes, you're the only one who can
Right.
change things at this
Right.
point.
Let's see. Let me ask. Okay, Ryan, I got a screen up here. Keeps going away. How come? Stop spotlighting me. Should I say stop spotlighting me?
No, because that was the camera. The problem right now is something has control of else besides Teams has control of the camera. And so the camera feed is not going out to Teams.
Well, remember when we lost the camera on Saturday? I mean, I know one thing that would go.
Yeah, we could try that.
What? Well, I'll log out completely.
Yeah, we can try that. Let's try it.
Huh?
Let's try it.
Let's see. I want to hang up, right? Yeah.
Correct. And then get back in and.
Yeah, I'll hang up and get back in.
Yep.
Well, no, John, if you're on audio phone, leave it on.
He's not. He's running through the Teams client. So.
Guys, we apologize. We had a lot of juggling to do, and we're going to get it resolved pretty soon. So bear with us. It's part of the COVID response.
Yep.
And I apologize.
Likewise. Okay, we have the camera feedback. That did it. Or at least I have the camera feedback here on the main control. So let me.
I'm seeing it. It came in real clear and then it went fuzzy, but it's still pretty good.
Right. Yeah, we should. Yeah.
I don't see a little miniature that I can click on it, so I've just got the blank screen with a stereotype of a presenter.
Yeah, hold on a second.
Okay.
When I do now, everyone should see the feed.
And John, the Zoom and tandem fields are all working, John. You got it. So go ahead and continue. John, can you hear us?
John, you'll have to unmute.
Can you hear me?
We can hear you now.
Perfect, John.
Yeah,
camera's working fine.
Yeah. Okay. Okay. Wait. Oh man, there's so many screens I'm hopping. Okay, just a minute.
John, if you're trying to narrate, we can't hear anything.
You can't hear me?
No, we can hear you. It's
now.
I didn't. Is there a problem, Doug, or something? No.
We couldn't hear you until just now.
Okay, you can hear me now, right?
Correct.
Yes.
Okay, I'm going to take this. I want to show a few things with this motor here. Okay. Can you see the red? Did you see this red thing lock in here?
Yes.
Okay, I just wanted to demonstrate the poles. So there's the top pole, and you can see the magnets grabbing the wheel. Also, I don't know if you can hear this, but can you hear the field at all in there or not?
Barely.
Okay. The power now is on to the synchronous motor. There's a starting motor at the other end. So you can see the shaft turning now, right?
Correct.
Okay, so I'm going to bring the tone generator up to synchronous speed. I don't know if you can hear that noise. That's the starting motor.
Yes.
There's power to the run motor. And now the whole tone generator is running. You can't hear it because it's pretty quiet. The other thing I wanted to show here a little bit is the spin down on this. I will play I'm not going to play nothing, but you'll see the sensitivity of the tone wheels. They're just millivolt outputs, about 4 millivolts. And, I got to, just a minute here. I'm putting power on the tube amp. I got to warm up the tubes. Okay, everybody heard the spin down, right? Like the dive bomber?
Yes.
I did.
Okay. The other thing I wanted to show right here, let's see, the can you see this hand moving on the clock or not?
Yes.
You can?
Yes.
Okay, just real quick. This is a 30s Hammond clock, and of course it's synchronous. But what I wanted to show was okay, the hand stopped. These clocks wouldn't start by themselves, so it's got a hand crank back here. And once I get to it, so there, you see it going around there, but I can also stop it, and the synchronous motor will run in both directions, and now the clock's going backwards. Anyway, probably nothing, but okay, let me see now. I think, yeah.
That would be the that would be the correct direction if you looked at it in a mirror.
Oh, okay. Hey, good point, Jim.
Nice.
I have a mirror in my bathroom that runs backwards. So you have to look at it in the bathroom mirror in order to see the time.
Okay, well, I'll zoom back out. Actually, I'll get back to my PowerPoint now. Okay, Ryan?
Okay.
Okay.
Wait 1 second. All right. So you have to share the PowerPoint again,
Let
John,
me see.
because
Yeah,
you,
okay. Open share tray. Okay, do you see it?
it's coming. Yep, now we do.
Okay. Okay, so that's the 6-pole motor. This is this is the gearing. The different gears. I don't have them all here. What I wanted to show was, say that top part is about 4 inches. The whole tone generator is 29 inches long. So it's one shaft. Oh, well, to make the shaft that long, would really be tough and alignment problems. So what he did was bust it up into 7 subshafts. I have that note on the bottom. And that's a little U-shaped coupling. And actually, those dogs, if you look to the side in the gear, they go in those holes. And they're really real free and loose. So, like when you start it up, you can hear them lock in. And then what's interesting, you couldn't hear it, but when you turn the tone generator off and it's coming to a stop, you hear clickety click, click, click as the different shafts, come to rest at different times, and it's those couplings. I might point out on the long shaft there, that right hand is just the end shaft where the starting motor is, and I just wanted to point out it's like a bending spring on a car, and that the starting motor goes in and the dog goes into that gear, it locks in and turns the whole tone generator. And then the other end, and that's the main drive coupling that I have, that goes to the synchronous motor, and then that's what keeps the whole shaft going all the time. Okay, there's this is just what you see in my camera is the top. This is the underside. So there's 91 wheels in there, spinning around at all those different speeds, like from around 900 to 1500 RPM. If you look close here, there's a metal strip. You look right below that. That's the main drive shaft. You can see some of the main gears. I've got some better shots. Okay, that's the top view. I'll talk more about it later, but those are LC filters, those 2 rows where you see the Sprague orange drop capacitors. I'll talk more about that later. And this over to the right where those caps are real close, that's the delay line I mounted on there. Okay, this is a shot of the run motor, which you saw, but a couple things to point out. There's this, the way Hammond did this tremolo and vibrato is a scanner, and that's where marked it here on the right, and that's driven from the one output shaft from the run motor. The run motor, the sync motor is right in the middle, and then to the left there is the main drive to the whole tone generator. And then, oh wait, I can point with this thing. I keep forgetting. And this is the main drive coupling. A couple interesting things here. This, with the 6-pole motor, you get pulsations on the line frequency, and he didn't want any of that into his tones. And, oh boy. So this comes off right here, this thin wheel, the drive shaft. This is a ball. If I took this apart, this is a ball and socket joint right here, and it's held in place by these two springs here, and then this spring kind of winds up. So with all those springs, he takes out a lot of pulsations of the synchronous motor. Okay. This is interesting. Now you can see there's 4 wheels that are rotated by the one main drive shaft gear. The main drive shaft gear is right here. And 4 wheels are turned by this one gear. So this would be, you know, a certain gear ratio. Another thing, he uses springs all over the place. This here there's 2 tone wheels on every shaft. So this is the one end in the bearing. The other end's over here. But the wheels are not like pressed on, or the wheels can spin on the shaft. And they're really spring loaded from this drive gear to the tone wheel. So if a bearing would lock up, or I've seen people drop the organs, and this is the mag pickup here with the chisel point, and this magnet goes in and jams against the wheel. This wheel will be locked, but the whole tone generator can still run because it spins on these springs. Kind of a neat design. Oh, how the thing is built. So basically there's 4 wheels in each bin, and 4 times, there's 24 of these bins, 4 times 16. You could get 96 wheels in here, but he's got 91. Some are dummies. But the point being, the way this thing's built is when they assembled it, this here is one bin. They start out on one end. There's 2 long shafts. And he just puts this bin on, and the next one, and the next one, until the whole tone generator is built. It was quite a, a lot of hand operation. The interesting thing is, but they really don't fail. If you got a problem with this coil and it's in the middle of the tone generator, guys have done it. So you got to take the thing apart from the end, boom, 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 until you get down to here. Okay, let's see. This is an interesting slide here. I tried to blow up to show the bearing lubrication. You got to look close, but there's 105 bearings in the tone generator and 105 cotton wicks. By capillary action, if you see this fine thread, oil gets down to oil this bearing. Right here is a trough that runs down the center of the tone generator, all filled with 105 wicks. And you oil this thing once a year, and like a half a tube of oil, and then it soaks the wicks. Oil goes down to the bearings, and the thing just keeps on running. Interesting thing. I mean, I've seen them in 1935. They first come out with these. Those things are still turning today. I was shocked. Mechanically, usually everything for me wears out. They have more problem with the electronics. Just simple, carbon resistors cracking, wax capacitors drifting. But this old tone generator. Oh, and if sometime you find one 20 years and then, well, it locked up, what you do, in case anyone gets one of these old timers, is you put naphtha or lighter fluid in the oiling cups, let it sit and soak, flush out the bearings, follow up with oil, and the thing's back in operation. I think that's it. The wicks here and the trough, and there's the main drive shaft gear here. and you know, you can see here the coupling too. You know, you saw it before, but you can see how the coupling, see, the dogs go right into the side of the gear. Okay.
Are they roller bearings, John?
No, bronze oil-like. Bronze oil-like bearings, yeah. The big thing, one thing to point out on this slide, I'll get into the drawbars, and this is how he gets so many tones. These duplicate pipes on a pipe organ. So you got the 16-foot pipe, the 8-foot, 4-foot, 2-foot, and 1-foot. So, you know, that's 1, 2, 3, 4, 5. And I'll show the tone with one key. You know, you can get 4 or 5 octaves of tones, and then these other guys in the middle here are odd footages, odd harmonics. The 2 5 1/3 foot pipe, the 2 2/3 pipe, 1 3/5, 1 1/3, and this is more of an eye chart thing to point out here. Is there's your here's middle C. Here's A above middle C is your kind of the standard 440 hertz, if anyone's into, you know, orchestras tuned to that. And then you can see 1 octave below is 220, 880, 1760, 3520. And then odd harmonics in between. Yeah, 160 frequencies with 67 tone wheels are on this chart. Okay, a little bit on how it really works. This is a diagram of one key. One key. So you have 9 key contact. Oh, by the way, in this talk, I use the word interchangeably, manual with keyboard. You know, today it's keyboard, but they call them organ manuals. So the keyboard, one key has 9 contacts, and there's 9 bus bars under each contact. So on the left here are your key contacts, and if you notice these fundamental, the harmonics, see, those are your drawbars right there. So every one of these drawbars here on the top goes to a bus bar to pick up a key contact. And basically, that's how it works. So the top line is the key contact, and then these bottom little things, my arrows on the right, are the bus bar outputs. So if you press a key down, you know, this goes down, makes contact with this key, and so on. And key contacts are a big problem. Hammond had, when they changed, these original were platinum and palladium, and they were the best. They didn't oxidize, but it was something that the bus bar was really steel, but it was a thin palladium wire. And believe it or not, they welded between the key contacts, spot welded the palladium wire to the bar. They did that till the 60s, but then they switched to gold plated, and that's another. They had a lot of problem with the plating. Let's see. So this is the actuator. You know, it'll come down, bend these leaves, and by the way, these are real long, and they got a nice wiping action. So, and especially with the old contacts, you get a little speck of dust. You just hit the key a lot, and it wipes the contact clean, and it speaks again. This is so. This would be if you're looking at the manual, the keyboard from the end view, and you would see all these contacts. This is a top view of one contact. So this square here would be where the actuator goes, and there's 9 of these then. And this is a little piece of platinum welded on to the key contact. And that's the platinum or palladium. They use platinum and palladium, makes contact with the bus bar that takes the outputs to the drawbars. So the concept you want to get here is this is coming from the tone generator to the keyboard, and this is one key. And then from this key, the outputs go to the drawbars. This is I drew this up. I don't know if this helps or not, but kind of gives you an overall. A couple things about the tone wheels and the tone generator. Frequencies 1 through 49 just have a resistor to ground, and then from 49, the upper frequencies use an LC resonance circuit for filters, and then the bus bars come into the bus bars under the drawbars, and then it comes to this is a high ratio amplifier, almost 1 to 500. So this is where you get all the gain. These outputs are 4 to 5 millivolts, and you get up into the voltage range here, which goes to a tube amp with a high impedance input. Real low millivolts, high voltage output, but real low impedance. We're talking here 30 to 40 ohms, and you know, up here you're getting into the mega ohms. Okay, real quick. Oh, so you saw resistors over here. Hammond did a lot for tone shaping. These resistors are on every key in series with the key contact are these resistors, and there's 100 ohm resistors, 34, 15, and they're different colored. And what they do at the real low frequencies, there's more resistance, so you don't get booming bass. And then at the high end, you cut out the there's resistors cut out some of the treble, and not much in the middle. An interesting thing, these are real low ohmage resistors. In the 30s, they didn't have low ohmage. He did it all with wire. Would you believe in a console keyboard, there's about 1,000 foot of wire? Because you figure there's 9 contacts under every key, 61 keys, and so you got a lot, and there's a couple feet on each wire. He got the resistance, real thin wire. He got the resistance by ohms per foot. Okay, it's I pretty much went through this. Let's see, signal. So basically the path is tone generator to key contacts, the key contacts to the 9 bus bars, the drawbars to a matching transformer, and the low voltage, millivolts RMS to about 2 volts, impedance going from about 10 ohms to a couple megs. And then the preamplifier is used to raise the voltage level. And then there's loading on this too. In other words, you know, you start pressing 5 keys down, you don't want the volume going up linearly. So the whole, the sound, the volume increases, but not linearly, which is real neat how they did that. Little bit on these LC tuned filters. I want to just, you notice these are new. I replaced all these. These had the old wax caps. Now, these are all coils. By the way, Hammond wound all their stuff. These are all, you know, it was a machine shop, really. They cut all their wheels. They even wound their power transformer. Oh, here's an oiling cup. There's 2 of these. So this is where you put the oil in. There's another one down here, and it goes to the wicks. This is an old wax cap that I took out. Now, most of these caps are like 0.1 microfarad. Some are 0.255. But this wax cap will absorb moisture, and I've measured it will go from 0.5 microfarad, 0.1 up to 0.5. It will get 5 times its output. So what happens is you're way off the resonance peak. And these coils, instead of putting out 4 millivolts, will get down to 2 millivolts, 1 millivolt. And although the organ doesn't change tune, it gets real, it's not brilliant anymore. It's not bright. So anyways, I put all these in. By the way, I got, these are all polyester Mylar. They won't drift now. And what I did was I got like 0.082, and I measured all of them. And then, you know, with the big tolerance, I was able to match, and I peaked every coil. So I was at the resonance peak to get the sharpness. You notice here, I couldn't sometimes get the exact. So there's another capacitor in parallel here that adds to get the resonant frequency. Okay, anyway, so you got the 1941 comes along. The organ came out in 35. The straight organ tone gets dull. I mean, so, even in churches, there's a tremolo to a pipe organ. They oscillate the chests. But Hammond, and it was just that straight, you know, dry tone. So anyway, Don Leslie came up with the mechanical solution with a rotating speaker horn and a bass speaker rotor. And he put the corner frequency in 800 hertz. And the rotors create an acoustic Doppler, increase, decrease in the frequencies by moving the sound back and forth. And you get the tremolo vibrato. By the way, the rotors turn at 400 RPM at high speed, and they have a low chorale speed, which goes at 48 RPM. This is a picture of what you see right here, the one I built with the 6x9 bass speaker. What's interesting here is the backside. Here's the 2-pole filter, and it's 12 dB per octave. It's an LC on each frequency. There's a coil here, coil here. If you look close, there's 2 capacitors. So basically above 800 hertz, all the frequencies go to the treble speaker. Here it's a compression driver, and all those below 800 hertz go to this bass speaker. And there's your motors, the high and low speed motors. So this is the 400 RPM motor. This is the low speed motor. It turns fast, but what it is this shaft pulls up. This is connected to the high speed motor. Power is dropped off this, and this is like a little tire, you know, big ratio and a small shaft, and you get the real slow speed here. This goes up. Real reliable, believe it or not. And there's a picture of, you know, the Leslie, the 2-pole filter is in here. This is just a shot, so you see how they taper the sound. The treble horn, there's 2 horns for mechanical balance. Sound only comes out one side, the other side's blocked. And the bass speaker, of course, is facing down, and you can see the bass comes out here, and you get the rotating tremolo on the lower frequencies. Then Hammond, he just never wanted to hear about the Leslie, and he wouldn't even recognize the design. So he had his engineers design an electrical Doppler, and basically it's a delay line that's scanned from beginning to end using a 6-pole, 16-throw air dielectric capacitor. Interesting, the rotor speed's 412. You notice it's right about the speed of the Leslie. And what happens is the delay line, you take a sine wave and you delay it, you just get a pure phase shift, which you get a decreasing frequency when it goes around 180 degrees. As it comes back, you get a recovery. So this is a picture of the scanner, and like if you take this, the starting point, you go around here, over here, you'll get the maximum phase shift. This rotates through, this is your switch, air capacitor. This is the maximum decrease in frequency. Then from here, as you come around back, you're increasing the phase, and then you're back to zero. The net effect is you get no shift in frequency, but you get a tremolo. Oh, that's the inside of the scanner. I just thought I'd show the outside, and you can see I marked here, that'd be 0. There's 180, and there's the wires that go to the taps on the delay line. And the delay line is just an LC filter, and these go to different taps. This is the maximum phase shift. Then you come around and back to 0. And this hole is where the other end of this drive motor comes in. There's a gear in here, and it spins the rotor. I think that's so this taps go to the delay line, and that's the farthest point down the delay line. Now this screw in here, these are just jumpers. So this jumper goes to here, this one goes to here. You can see this at the top. So, it's the same point, but you're coming back. Okay. I had to throw this in, everybody fail safe. They didn't want to, all the signal comes through that one pole. So this is fail safe, triple redundancy. You can see the single pole shaft, and he's got 2 carbon brushes. And they go, I've got them off, but they go on that shaft. You never lose the vibrato signal. This is the shield, this is low level shielded line that goes back to the amplifier. There's the delay line. You can see the LC networks. These are all the coils here. Oh, I got them marked. There's all the caps. And these are the wires coming off various points of the delay line that go back to the scanner. Yeah. That's just a little schematic of, the vibrato, electronic. Well, this shows both, because you can actually, have them both going. The vibrato signal coming off the scanner, going back into the amp. This is the vibrato input down the delay line, comes out here down the power amp. If you have this switched off, then you can go to the acoustic, which is the Leslie. Okay, that's about it. I think we'll zero in on the drawbars. I'll give a little tune here. These, so you can see, these are the drawbars. You'll see me moving them. But there's 9 bus bars go across here, come out here. This is the matching transformer. These wires are the 9 bus bars coming off the keyboard. The keyboard's back here and going to each drawbar. And the drawbar, I didn't, the bus bars in here go to taps on, well, not on this one, but on the consoles, taps on the matching transformer. And when the drawbars are all the way in, you're at 0 or at ground. And then you just keep going up each winding, and you get more volume out of each. And that's basically how it works. This is a pedal drawbar. These are the connectors. I think I got about 90 wires, how I connect the keyboard to the tone generator with those cinch mini connectors. think that's it. Just let's see, a couple of tunes. I don't know how. This is about it for the PowerPoint. Ryan, we'll go back to the camera, and then
Okay.
The tone generator. This is only one keyboard. The tone generator in my Hammond is the same tone generator, but I got the two keyboards, the pedal board, in the Leslie. So I'm going to run downstairs. I got wires here. I'm going to hang the mic halfway down the basement steps. And when I'm done here, and we'll play a little tune. If you hear a thud, well, don't worry about that. Okay, Ryan, can we try to get the camera now?
Yeah, camera's up.
Okay. Let's see. What do I have? How do I get the camera to? Boy. See, I can't see. I think I'll go out again and reattach, okay?
We can see it fine.
Yeah, but I want to zoom in on the drawbar so you see what I'm doing. Can I, where's the Teams?
John, maybe you want to maybe you just want to demonstrate how it plays, and
yeah. Ryan, let me try to hang up and just restart, okay?
Please,
like
John.
Huh?
John, we're running close to the end.
Could
you just do your part and wrap it up, please?
Okay. Well, okay. Crosstalk and hum, but anyway, all the drawbars are in. One thing I wanted to point out is this is one note, C. There's the same note, one octave up. I'm just going up one drawbar, another octave, and then with one key. I'll show you some of the odd harmonics. Okay, I've only got one drawbar out, so I'm playing the C chord, C, E, G, C, E, G. I can hold the C note, and then with the next drawbar, I'll pull out the third. Here's the drawbars with one note, and now, so I'm just showing how you can blend harmonics with this. Okay. Now the other thing, for the acoustic Doppler, rotor that you heard, believe it or not, I can believe it, whether you call it Murphy's Law or what. Ryan and I did it the first time this happened, but so I do the same thing, and I turn my delay line on, the electric vibrato. Well, here it is. Anyway, it doesn't work. You can hear the scanner going, and I'll be darned if I can find it, but it does work. Anyway, Ryan, let's see. Can you hear me then, Ryan, now?
Yes.
Okay. I don't need to put that picture on, do I?
No.
Okay. Okay, I'll play a short tune. That'll be it. Give me a couple of minutes here. Got to take the microphone down and all these wires. Okay.
I just want to go ice skating.
John, I'm going to have to ask you to bring this to a close, please. Ryan, I'm going to have to ask you to take control and bring up the last slide where Debashis can close the meeting, please.
Yep. 1 second.
And Debashis, you want to make any closing remarks for the section?
Yes. Thank you all for joining tonight. It was a great presentation. I'd like to once again congratulate all the science fair winners. Congratulations. A great job. It was very difficult doing virtually, but you did an awesome job. And once again, congratulations. Also, congratulations to all the incoming officers for ISAC position for next year. So it'll be great working with you next year. And congratulations to all, and good job on that. And thanks for everybody for hosting the elections electronically. That was done great also. So congratulations again. And thanks to John Mihevic. It was an awesome presentation. Great. We learned about a lot of organs today, and also music was great. Thank you very much. So in conclusion, thank you for joining us once again. And we're going to have one more in May presentations for Cleveland section. So hope you join us for that. And please watch our website and also look for our newsletters to come out for the May's presentation. So thank you all and good night, and hope to see you next month and also in the coming months. Thank you.
Brian, thank you very much for hosting, and good night to all.
Yep. Thanks,
Good night,
everybody.
everybody.
Good
Good night.
night, all.
Good night.